In this tutorial, we're going to take a look at some applications of sinusoidal functions and their derivatives. And we're going to start with a pendulum. A pendulum's motion can be modeled by the equation h of t equals a cos, and in brackets 2 pi little t over big T. Now, t represents here the time, and so h of t would represent the height at that time. And now I've said centimeters here. You could change the units as long as the height and the length of the pendulum are both in the same units. So if you want to be inches or meters, something like that, that would work. In the example I'm going to use in the next page, I'm going to use centimeters for the length, for the units for the length. A represents the amplitude, and amplitude is the distance between the resting position and the far right or left movement. So that's the amplitude. And the capital T is the period of the pendulum in seconds, and you could change this to a different unit if you wanted, but we would normally for a pendulum use seconds for the time. The period of a pendulum can be found from this formula. Capital T equals 2 pi times the root of, and this is an L being the length of the pendulum, divided by 9.8. 9.8 is actually the acceleration due to gravity on the surface of the planet Earth. It's 9.8 meters per second squared. That's where the 9.8 comes from. In this example, we're going to take a look at a pendulum, and we're given its length as 0.8 meters and amplitude of 10 centimeters, and find two things: the maximum speed of the bobbin A, and then the first and second time when that maximum speed occurs. Now notice that the length and the amplitude are in different units, meters and centimeters. And because that 9.8 meters per second squared is meters per second squared, it'd be best to leave these both in meters. So when we need the 10 centimeters, we're going to convert it to meters. So we want to find the length of the period of the pendulum. So L here is the 0.8 meters. So I'm going to bring my calculator over here. And so we go 2 pi, so 2 pi times the square root of 0.8 over 9.8. And so we get a length of the period as 1.795 seconds. So that's where this 1.795 seconds comes from. So the other formula on the previous page, the height at any time is, now the amplitude, this is the amplitude here, so 10 centimeters is 0.1 meters. Cos 2 pi t over the t is time, little t is time here. And this is the period, the capital T, the 1.795 seconds. Now, I'm going to simplify this instead of leaving it as 2 pi over 1.795. So it's 2 pi divided by 1.795. So this constant here is almost exactly 3.5. It's 3.500, and then the next digit isn't a non-zero until we get to this decimal place. So I'm going to simplify this to 3.5 t, and so that's the height. Now the speed is the rate of change of distance. So the rate of change of height here would be the derivative. So that's why we need the derivative of this function. So the derivative, okay, so we start with a 0.1, and the derivative cos is negative sine 3.5 t, and because this is a 3.5 t and not just a t here, this is a bit of chain rule, we need to multiply by the derivative of the 3.5 t, which is the 3.5 here. It's a negative here because the derivative cos is negative sine. Now I'm going to simplify this. If I multiply the 0.1 by the negative 3.5, I get negative 0.35 here, and then sine 3.5 t. So that's my speed function, my derivative. So the maximum speed, well, what's the highest value of this? So because I want to find the maximum value of this, or if I want to find the minimum value, I would look at the next derivative. So we need the second derivative of this function. So the second derivative would be the negative 0.35, and then times the derivative of the sine 3.5 t. The derivative of sine is cos, so cos 3.5 t, and again multiplied by the derivative of 3.5 t, which would be 3.5. Now simplifying, I'm going to multiply these together, so we get negative 1.225, and then cos 3.5 t. And I want to find the maximum value of this, so I set my next derivative, the second derivative, equal to 0. So I'm going to set that equal to 0, and I want to solve for t here. So first I want to get rid of this negative 1.225. So divide both sides by negative 1.225. And of course, these will divide out. And so we would then get cos 3.5t equals, and this would be 0. So where is the cos 0? I'm going to bring in my unit circle here. And I've drawn a couple arrows here, and actually maybe it's best if I erase those. Back to the beginning here. So, and I'll use my pen. So this is the unit circle. It shows where the cosine, what the cosines and sines are of the special angles. Cosine's the x coordinate, sine's the y coordinate. So for example, this is pi over 6. The cosine of pi over 6 would be root 3 over 2. The sine would be a half. Now we're looking for where the sine is 0. So we're looking for x coordinates that are 0. So we get 1 here. So pi over 2. So that's a rotation of pi over 2 to there. And then down at the bottom here, there's another x coordinate of 0 right there. So a rotation around to here, which is a rotation of 3 pi over 2. And then if I wanted one more rotation, another color here, then we could also do this. We could go a full revolution, kind of skip there a bit, and around to there. That would be 5 pi over 2. So it actually goes pi over 2, 3 pi over 2, 5 pi over 2. If I kept going for another down to the bottom, it would be a 7 pi over 2. And so that's where I get these values. So I'm going to write on my presentation here. So the inverse cosine is 0. These values here will be the pi over 2 that I showed first, 3 pi over 2, 5 pi over 2, etc. I could list more if I wanted to. Now, I'm trying to solve for t here, so I could divide by 3.5 to get the t alone. Okay, those divide out. Now, dividing by 3.5 is the same as multiplying by 1 over 3.5. Remember, dividing by a number is the same as multiplying by the reciprocal. The reciprocal of 3.5 is 1 over 3.5. So in the next line, that's where I get my time, is 1 over 3.5 times all these angles, these rotations. Actually, let's get rid of my writings here. Now, the reason I want to write it like that is because this actually simplifies nicely. 1 times pi or 3 pi or 5 pi is pi, 3 pi, 5 pi. And in the denominator, 3.5 times 2 gives us 7s for all these denominators. So it's a fairly nice little, relatively simple value. And so I want to evaluate each of these. So pi over 7. So we get about 0.45 seconds. And then 3 pi over 7 would be about 1.35 seconds. And then 5 pi over 7, next one, etc. So that's where our values come. Now, this is 2.24. I'm going to write 2.25. And the reason I'm going to do that, actually, let me just bring those values up here. Next line here, is because I've done a little bit of rounding here. Remember, the period was 1.795 seconds. So if I take my 0.45 here, 0.45, that's the beginning, whoops, 5, and add the length of a period, the 1.795 seconds, 1.795, okay? So like this is almost exactly the same as this. There's a very slight difference. So it would round to 2.25. Okay, so that's why I'm writing 2.25 instead of 2.24. Now, so those are the times maximums, or the maximums and minimum values of this occur. So let's start substituting these in place of time to find what those speeds are. We'll see some maximums and some minimums. So putting 0.45 in place of time, we get negative 0.35 times, and this would be 3.5 times that 0.45 there. So, and maybe I'll show one or two in these in the calculator. So in the brackets there, we'd have 3.5 times 0.45 seconds. Whoops, I want to do the 4 there, 4.5. So it's going to be 1.575 in the brackets here. And actually, maybe I'll bring that one up. So we would, and of course, you want to make sure that calculator is in radian mode. So negative 0.35 at the front here, sine 1.575, close bracket. And so it's almost exactly a negative 0.35. And that gives us h prime of 0.45 is negative 0.35. So that's a negative, so that would represent a minimum, if I think of a negative as the minimum. So let's do the next one, the 1.35. So if we put 1.35 in place of time, so here's my 1.35 seconds. So multiply that together and we get 4.725 here. So sine of that times the negative 0.35. And it gives us positive 0.35. Maybe I'll demonstrate that one as well here in the calculator. So actually I can negative 0.35, actually do the whole calculation straight like this. And then if I want to do 3.5, like the whole thing, times 1.35 seconds. So there's my 0.35. It's positive in this case, so we found a maximum. And then so let's do the next one, the 2.25. So if we do that, we get negative 0.3. So it's alternating back and forth between negative 0.35 and positive 0.35. So the maximum speed of the bob is 0.35 meters per second, and it would occur at, and see this is the first one at 1.35. If we want to find the next time, that would be the simplest way to do that. It's the very next one after the 2.25. But you see, if we take this 1.35 seconds, that number right there, 1.35 seconds, and add that period 1.795. So 3.145, so 3.15 seconds approximately. So that would be the maximum speed. In example 2, in the last example, we're told the residential and commercial voltage in the UK is 230 volts with a period of 1/50th of a second. So one full cycle occurs in 1/50th of a second. It cycles through pretty quick. A says create a function to model the UK's energy supply, the voltage. What's the rate of change at 0.1234 seconds? I just chose an arbitrary time. And then C is determine the maximum rate of change of voltage in a time which it occurs. So because it's 230 volts, it actually cycles between positive 230 and negative 230. So that's the amplitude. So the voltage at any time is 230 times the sine, and we're told the period is 1/50th of a second. So to get the constant with the t here, we divide 2 pi, the standard period of a sine or cosine function, by the actual period, the 1/50th. And remember, you simplify this by you're dividing rational expressions. So we take the top, the 2 pi, and you multiply by the reciprocal of this, would be 50 over 1. And so 2 pi times 50 would be 100 pi. So the model, the voltage at time t, is 230 times the sine of 100 pi t. So that's the equation we're looking for in A. Now, you could use a cosine function here too. It just depends on whether you want to start at the middle or a maximum point or a minimum point. So you could theoretically use cosine here too. You don't have to just use sine. I'm assuming we're right in the middle, okay, for it to use sine because that's where sine starts. It will go up to 230 volts and then down to negative 230, etc. B asks, what is the rate of change at 0.1234 seconds? So we need to differentiate this to find the rate that the voltage is changing. So for B, so that's our function, and we want to find the derivative. So the derivative of a sine function is a cos function. So we go cos 100 pi t, and then multiply that by the derivative of the 100 pi t. 100 pi is the coefficient of the t, so that's the derivative. And then, to simplify it, we'd multiply the 100 pi by the 230. So 230 times 100 would be 23,000. And don't forget the pi here. And then cos 100 pi t. So we want to find the voltage at 0.1234 seconds. So in our calculator, we would type in 23,000 pi times the cos of 100 pi multiplied by that 0.1234. I'll close my brackets. And so that's where I got my 34,809.9 volts. That would round to 0.9, volts per second. It's the rate that the voltage is changing. So that's my answer statement for B. And C now asks, determine the maximum rate of change of voltage and a time for which it occurs. So we want to find how fast this rate of change is changing. So it's a rate of change of a rate, or a rate of change of rate of change. So in order to do that for C here, okay, so there's our derivative from over here. To find the maximum and minimum value of this, we would need the second derivative, the next rate. So the second derivative would be 23,000 pi, and now we need to differentiate this cosine function. Remember, the derivative of cosine is negative sine, so we go negative sine 100 pi t times the derivative of what's in here, remember chain rule, and the 100 pi is the constant of the 100 pi t, so that's why we're multiplying by 100 pi. And so we want to simplify this now, so we'll stick this negative in front. 23,000 times 100 is 2,300,000, and then pi times pi is pi squared, and this sine 100 pi t. So that's the second derivative, and to find out where the maximum minimums occur, we will want to set this equal to 0. So very similar to what we did with the pendulum one on the previous page. And so I would actually be doing this. I didn't put this in my presentation here, but I would divide out this big constant here, 2.3 million. Make sure I write enough zeros here. 1, 2, I need 5 of them. Pi squared. So we're going to divide by that on both sides. 1, 2, 3, 4, 5, and then pi squared. So that's what we're doing. And of course, these divide out over here. And so in the next line, you're going to see sine 100 pi t equals 0, because 0 divided by this, of course, is 0. So let's get rid of that. And so we get sine 100 pi t equals 0. And I want to solve for the 100 pi t and then the t. So 100 pi t would be equal to the inverse sine of 0. And then I'll divide out the 100 pi to isolate for t. So t is 1 over 100 pi times the inverse sine of 0. And, well, where is the sine of 0? We could go back and look at the unit circle. Sine is 0 at every multiple of pi. 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, etc. Okay, so we need the unit circle for that. So I listed the first 3 here. Again, I could do 3 pi, 4 pi, 5 pi, whatever. So now what happens here when we multiply the 1 over 100 pi by each of these, see, this pi divides out with all the pi's. And so when you do that, well, of course, 1 over 100 pi times the 0 is 0, but the second part here is that this pi would divide out, so there'd be a 1 there to multiply by the 1 over 100, so that's why it's 1 over 100. For the second one, see, the pi would divide out with this, and so you would actually have 2 over 100, which of course reduces to the 1 over 50. Okay, so that's the first 3. And I'm just getting rid of my, there we go. So that's the first 3 times. Now I'm just going to change it to decimals so it's easier to work with. This, of course, would be 0.01, that would be 0.02, be 0.03, 0.04, etc. And so let's bring the calculator back here again. Now those are the times the maximum occurs. We're trying to find the maximum value for the rate of change of voltage. So I'm going to put 0, and actually maybe we'll write this out first. So in our voltage function, I almost want to call it velocity, voltage function, we're going to put 0 in place of time, and then the 0.01, 0.02, etc. So this is what the calculation would look like. We would go 23,000 pi times the cos of 100 pi times 0. And that's the first answer there. And so that's our rate. I actually showed a little more in the presentation here. 100 pi times 0, of course, is 0, and the cos of 0 is 1. So it's actually, the exact value is 23,000 pi, which I calculated with the calculator there. And so that's where the 72,256.6 volts per second comes from. So the put my concluding statement up here. The maximum rate of change of voltage is 72,256.6 volts per second, and it occurs at 0.01 seconds, 0.0 seconds at any of those. So that's the rate of change of voltage at 0. So the maximum rate of change of voltage is the 72,256.6 volts per second, and it occurs at 0 seconds. Now, if I showed what happens at the 0.01, 0.02, let's do that. Pretty easy in the graphic calculator because you can actually just replay that. So I'm going to put 0.01 in, 0.01. Missed my decimal there. Point. There we go. Close the bracket. 1, close bracket, there we go. So notice that, oh, I missed a 0 there, didn't I? Let's go back. 0 point, and then I need a 0, 1. There we go. So notice that one works out to negative well, just the opposite of this. So that would actually be the first minimum. And then, of course, if I went to the 0.02, just need to edit this to a 2 here. We're back up to the positive 72,000. So we have a maximum here, a minimum here, a maximum here, and it just alternate. It's a sinusoidal function, so you should expect that back and forth. So that's the where a maximum occurs and what it would be. And that's the end of the tutorial.